And so when we're using the properties of radicals, what it's going to say is, if I have the square root of A divided by the square root of B, it's going to be the same thing as taking the square root of A divided by B. So you could bring it under a single radical. You could have a single radical, take it apart. That's what we did previously. Or you could have two radicals and bring it back together. You could take it apart, bring it back together. So that's what this is. I've got two radicals, and what I notice is if I could bring them together, 2 divides 50 evenly already. So that says I can reduce the size of what's under the radical. By the way, if I couldn't, then it wouldn't do me any good to bring it under the same radical. But so the first thing I look at is, if I bring it under a single radical, does it reduce? Well, the answer is yes. This turns into the square root of 25, and then we know that the square root of 25 is 5. So it's simplified, and that's what the goal is. Anytime you're manipulating radicals at all, you're looking at simplification. That's any reason why you would manipulate it. You would manipulate it so you could simplify. So if I look at this, I've got square root divided by square root. I have, if I notice 10 divides 30, y takes out that y. So that says if I bring them under a single radical, this will be 30 y to the 5th divided by 10y. And now the next step is to reduce what's under the radical. And I notice that 10 goes into 33 times. Y takes out one of those 5, gives me a y to the 4th. And the denominator is 1, so the denominator is completely gone. So I'm going to be left with the square root of 3y to the 4th. And that radical can be simplified. I'm dealing with square root. So I have the square, which is y to the 4th, and the leftover, which is 3. Square root of y to the 4th is y squared, and the leftover is square root of 3. What happens when you use this stuff, really, it's usually because you're manipulating formulas. That's why. Simplifying so you can move forward. So it's more of interest to people who are going to be taking college algebra, calculus, physics, some of the sciences, than probably for many of you, because at which point, if I'm dealing with numbers, I can just put the sucker in my calculator and get it to 8 decimal places. And it's happy. Now, the next one is cube root. And I notice that 2 divides 54, and I can take a y out, so I can bring it under a single radical. But I do notice that the first radical has a coefficient. So I'm going to break this off as a 5 over 1, because that's what it is. And then I'm going to write as a single radical what's left over. This is 54 y to the 7th over 2y. And this is a cube root, so I have to be very careful. So if I left it a square root, I'd have a completely different answer. So this is a 5 over 1. Now 2 divides 54 27 times, and y takes out one of those 7 y's, leaving me with a y to the 6th. So I'm just left with the cube root of 27 y to the 6th. That's also over 1 because the denominator is gone. And 27y to the 6th is a cube. So this is 5 times cube root of 27 is 3. Cube root of y to the 6th is y squared. And so you're left with 15 y squared. Nice, clean, and simple. Now we've got a fourth root. But I noticed that I've got A's and B's in the denominator, A's and B's in the numerator. That means if I put them under a single radical, I can reduce things down. So that under a fourth root, I'll have a 48 a to the ninth b over a b to the negative 3. And that negative exponent we know we can bring up so that this becomes the fourth root of 48 a to the ninth b times b cubed all over a. The a's reduce, so this gives me an a to the 8th power. And the b's are going to combine. That's going to give me a b to the 4th power. So that under the radical, I no longer have a denominator. I'll have a 48, I'll have an a to the 8th, and I'll have a b to the 4th. And now I'm going to need to simplify. So I have the fourth root, and a to the 8th is a perfect fourth, b to the 4th is a perfect fourth, but 48 is not. So I look for my handy dandy powers table to help me out. For 48, I'm now looking at the 4s. Well, 48 is smaller than 81. My only choice is 16. As does 16 divide 48 evenly? Yeah, it's 48. 48 is going to be 16 times 3. So I'll have the fourth root of 16, which is 2. The fourth root of a to the 8, which is a to the 2. The fourth root of b to the 4, which is b to the 1. And I'm left with the fourth root of 3. This is all just manipulation. And these worked out rather nicely. And I know I can use this process when I've got things in the denominator which will divide with things in the numerator. However, I can have things that do not. And here's what the issue ends up being. Suppose I have 1 over the square root of 2. Well, first of all, 1's not under a radical. And even if it were, 2 doesn't divide 1 evenly. So I've got a problem. I can't get rid of the denominator. I can't get rid of the radical in the denominator. Now, with today and the technology, if I were dealing with this in particular, I wouldn't have to worry, because since it's a number, if I would take 1 and divide it by the square root of 2, I could come out with this guy to, I know for sure, 3, 6, 9 decimal places of accuracy. I don't know whether that 2 is a 2 because the number behind it is smaller than 5, or if it really would round to whether it is a 1 which got rounded to a 2 because the number behind it is 5 or bigger. But I know for sure that this is accurate to 9 places. The question is, how many places do you need? Well, as many as you need. If you're trying to land a space shuttle on an airstrip, in California or Florida, you probably need a very high level of accuracy. Because if you're off by a little bit, you could find yourself in the ocean somewhere and maybe not being able to be retrieved. So you might have to have much more accuracy than that. And computers handle that very well. But for most purposes, 9 places should be more than enough. But BC, before calculators, that meant that what you were going to do is you had to, this says this, take the square root of 2 and divide it into 1. That makes no sense. How in the world do you do that? Well, you'd have to work it out, and you'd have to figure out, I'm not going to go through it the way we used to do square roots. We would start with tables, and we would do something like it would be extrapolation. So in other words, what you would do is that 2 is a square. If 2 is a square, my list of squares are 1, 2, 9, that's 3 squared, 4 squared, etc. If essentially, or 1, 4, 9, if I am looking at the square root of 2, and 2 is a square, 2 is somewhere between 1 and 4. That means if I look at what produced it is between 1 and 2. And then what you would do is say, well, 1 times 1 is 1, so that's not good. Then you would take 1.1 times 1.1, and you'd keep doing that until you would have, essentially, you'd be bigger than 2. And then you back it off, and you'd have 1 place of accuracy. Then you would take 1 point, and let's see what square root of 2 really is. It's 1.14. So in other words, I'd have to take 1.1 times 1.1, 1.2 times 1.2, 1.3 times 1.3, 1.4 times 1.4, 1.5 times 1.5 is bigger than 2, so you know that 1 decimal place of accuracy is 1.4. Now, once you did 1.4, then you do 1.41 times 1.41, 1.42 times 1.42, 1.43 times 1.43, until you got bigger than 2. In this case, you don't have to go to 1.42 to say, okay, it's 1.41. Then you take 1.411 times 1.411 until you got bigger than 2, which would be 1.415. Then you'd back up to 1.414. And you would continue to do that by hand until you got as many decimal places of accuracy as you needed to do. BC, before calculators. Before calculators. So if you think about it, if you were working before calculators, you had to have a method which would make that would make it easy to do. Because if I look at the square root of 2, this decimal division would be 1.414213562 divided into 1 point. And if you remember decimal division, you would move this decimal point over here, and then you would add as many zeros as you need and move the decimal point there. You'd have that big number into that number. That's decimal division. Well, you don't want to do that either. BC, before calculators. So what did they do? They did something called rationalize the denominator. So in other words, they took the radical out of the denominator to make life easier. Now, we only do it today when we're working with formulas. and we're simplifying and manipulating formulas. If I have numbers, I can get 9 places worth of accuracy. I don't care. 9 is usually enough. But now we do it to manipulate formulas. So those of you who are going to be taking college algebra will actually be rationalizing the numerator in order to manipulate the formula. Those of you going to be taking calculus, you'll be doing the same thing, because in order to get the formula out, you're going to have to rationalize either the denominator or the numerator in order to simplify things. For us, it's just an exercise in understanding what rationalize the denominator means, which means take the radical out of the denominator. Now, how could I get rid of the radical? By making the denominator a perfect square. The concept is this is 2 to the 1. In order to be a square, I need a 2 to the 2. So I would multiply the denominator by a 2 to the 1 and the numerator by a 2 to the 1. I'm multiplying by 1. I multiply a fraction by 1, and what does it do? It changes the appearance of the fraction, but not the value. I take 1/2 and multiply it by 3 over 3. I get 3 over 6. It's still 1/2, but in a different form. This is still 1 over the square root of 2, but in a different form. I will get 1 times the square root of 2 over the square root of 2 times 2, which is 2 to the 1 times 2 to the 1, which is going to be the square root of 2 over the square root of 4, which is just the square root of 2 over 2. So you can say, well, what difference does that make? Well, if I'm doing a division, this says now take the whole number 2, divide it into the square root of 2. 1.414213562. That's a very easy division that you can do by hand. This came about because people had to do this stuff by hand. And if you had to do it by hand, you're going to find a shortcut way to do it. Today, we take our calculator, get it to 9 places, and that's great. Then you needed another way around it, and it was called rationalize the denominator. So if you did this all the time, you'd find a way around the problem if you could. And that's what, and they did, to make their lives easier.